We've talked about groups and rings, and today we're going to introduce fields. But we start with congruences. So the fundamental definition is integer a is congruent to integer b mod some positive integer m if m divides a minus b. Now, congruence mod m is an equivalence relation. That means it is reflexive, symmetric, and transitive. And so it divides the integers up into equivalence classes, which are called congruence classes. So the congruence class a plus mz is all integers b that are congruent to a mod m. So this is, in fact, an infinite arithmetic progression. It contains a plus m, a plus 2m, a plus 3m, and so forth, a minus m, a minus 2m. It's doubly infinite arithmetic progression. And z mod mz is the commutative ring of congruence classes. This is a finite ring. And it consists of mz, 1 plus mz, two plus mz, up to m minus 1 plus mz. So this ring has exactly m elements. And we say that a set of integers r1, r2, maybe up to r sub, started maybe r0, r1, r2, up to r sub m minus 1 is a complete system of residues modulo m if we could also choose these as the representatives of the m different congruence classes. And recall that mz itself, which is the congruence class of 0, is just the set of all multiples of m. Recall that a and m are relatively prime if the greatest common divisor of a and m, which we usually just write as am in parentheses, is equal to 1. And we can make the following observation. If a and m are relatively prime, and a is congruent to b mod m, then b and m are relatively prime. And the proof of this statement is very easy. If A is congruent to B mod M, then A minus B is divisible by M. It's MQ for some Q. So you could write B is equal to A minus MQ. If an integer D divides B and M, then D divides A minus MQ and M. And so D divides A. So D divides A and M, so D has to equal 1. And it's a nice exercise to prove everything that I just said. Prove this. So it follows that it makes sense to say that the congruence class A plus MZ is relatively prime to M. So this is a congruence class if A and M are equal to 1. Because by what we just showed, if one element in a congruence class is relatively prime to the modulus M, every element is. So we let Z mod MZ cross or star be the set of all congruence classes in Z mod MZ relatively prime to M. And we let, or we define a very important function. It is called the Euler. It's spelled E-U-L-E-R, it's pronounced Euler. Phi function, Greek letter phi of M, is the number of congruence classes that are relatively prime to M. So the Euler phi function, which is one of the fundamental functions in algebra and number theory, is the number of congruence classes that are relatively prime to M. Let's look at some examples. Suppose I take the modulus 2. So Z mod 2Z just consists of the even numbers and the odd numbers. What numbers or what congruence classes are relatively prime to 2? Well, it's just the odd numbers. Every odd number is relatively prime to 2. So 1 plus 2Z, there's only one congruence class in Z mod 2Z star. And so phi of 2 is equal to 1. There's just one congruence there, congruence class there. Suppose I take M equal 3. I look at 3 mod Z mod 3Z star. So any number which is congruent to 1 or 2 mod 3 See, a number is not relatively prime to 3. 3 is a prime number. The only numbers that have a common factor with 3 are numbers divisible by 3. So you have to throw away the 0 congruence class, but anything which is 1 or 2 mod 3 is relatively prime to 3. So phi of 3 is equal to 2. Suppose we take the integers mod 4. So any even number has the factor 2 in common with 4. So the congruence class of 0 and the congruence class of 2 have to be thrown away. But anything which is 1 mod 4 or 3 mod 4 will be relatively prime to 4. So phi of 4 is also equal to 2. What about m equals 5? So a number is not relatively prime to 5 if and only if it's divisible by 5. The only numbers that are divisible by 5 are in the congruence class 0 plus 5z. So the other 4 congruence classes are relatively prime to 5. And phi of 5 is equal to 4. We'll do one more. What congruence classes are relatively prime to 6? Well, 6 has a lot of divisors. Any number that's divisible by 2, 3, or 6 has a factor in common with 6. So anything in the congruence class, well, anything that's congruent to 1 mod 6 will have no factor in common with 6. 2 plus 6z, they're all even. They have a factor 2 in common with 6. 3 plus 6z, everything in that congruence class has a factor 3 in common with 6. 4 plus 6z, everything in that congruence class is even, has a common factor with 6. 5 plus 6z, anything there is relatively prime to 6. So there are only 2 congruence classes, mod 6, which are relatively prime to 6. So phi of 6 is equal to 2. And if you look at this function, it's kind of erratic. It jumps up and down. It's not monotonically increasing, for example. 1, 2, 2, 4, 2. I defined a complete system of residues modulo 6, modulo m, a reduced system of residues modulo m is a set of exactly phi of m, or the phi function of m, integers 1 from each congruence class relatively prime to m. So for example, for m equal to 3, a reduced system of residues would be 1 and 2. Or 8 and minus 8. Or 76 and 77. Let's make it more interesting. 76 and 104. And 8 is congruent to 2 mod 3. Minus 8 is congruent to 1 mod 3. So there's 1 from each residue class relatively prime to 3. 76 is congruent to 1 mod 3. 104 is congruent to 2 mod 3. So these are all examples of reduced systems of residues modulo 3. Let's go back to our fundamental theorem about linear congruences. Let A and M be integers with greatest common divisor D. The linear congruences, AX congruent to B mod M, is solvable as a solution if and only if B is divisible, means congruent to 0, modulo D. And in the case when the congruence is solvable, if B is congruent to 0 mod D, then the congruence, that congruence, has exactly D pairwise incongruent solutions mod M. So let's look at another example. Suppose we take the congruence 15x congruent to 20 mod 35. So A is equal to 15. M, the modulus, is 35. D is the greatest common divisor of A and M, which is the greatest common divisor of 15 and 35, which is 5. And B, which is 20, is divisible by 5, is congruent to 0 mod 5. So this congruence has exactly 5 incongruent or different solutions. So let's try to find them. So if 15x minus 20 is congruent to 35, if this equals 35 for some y, that's the same if you divide by 5 as saying 3x minus 4 is equal to 7y mod 5, which is the same as saying, sorry, not 7y, is equal to 7y, which is the same as saying that 3x is congruent to 4 mod 7. We can find a solution of that by trial and error. X equals 0 doesn't work. X equal 1 doesn't work. X equal 2 doesn't work. X equal 3 doesn't work. X equal 4 doesn't work. X equal 5 doesn't work. X equals 6 does work. If we let x equal 6, 3 times 6 is 18, and 18 is congruent to 4 mod 7 because 18 minus 4 is 14, is 7 times 2. So x equals 6 is a solution. And if x is a solution, So we have infinitely many different solutions. Anything congruent to 6, so X is a solution if and only if X is congruent to 6 mod 7. So what are the numbers 6 mod 7? 6, 13, 20, 27, 34, 40, 47, and so forth. But these, the first 5, these are in different congruence classes modulo 35. So just to summarize, we have that 15x is congruent to 20 mod 35, if and only if 3x is congruent to 4 mod 7, if and only if x is congruent to 6 mod 7. We're looking for solutions mod 34, if and only if x is congruent to 6, 13, 20, 27, or 34 mod 35. So we have D equal to 5 solutions mod 35. Now there's a very special case when we know that a congruence has a unique solution. So the special case is when D, which is the greatest common divisor in A and M, is equal to 1. So in that case, AX congruent to B mod M has exactly 1. So a unique solution modulo M. And a more special case is when M equals P, a prime number. So if you take any prime number P as your modulus, then if A is an integer which is not congruent to 0 mod P, then A and P are relatively prime. If you take a number A, if it's not divisible by P, then it's relatively prime to P because the only factors of a prime are 1 in itself. So if you take a number A and P certainly have a factor 1 in common. They have a factor greater than 1 in common if and only if A is different from 0 mod P. So if A is any number congruent to 0, not congruent to 0 mod P, then the congruence AX congruent to B mod P has exactly 1 solution modulo P, exactly 1. If we restate this in the language of congruence classes, so let's restate this in the ring of congruence classes mod P. For all A plus PZ not equal to PZ, and B plus PZ, a congruence class, there exists a congruence class X plus PZ such that A plus PZ times X plus PZ equals B plus PZ. So you can solve any equation, any linear equation in congruence classes. So let me express this in a more algebraic way. Suppose that R is a commutative ring, and element A in the ring is called a unit if there exists an element X in the ring such that AX equals 1, the identity. So remember, a commutative ring, it's an abelian group under addition. You can multiply. The multiplication is commutative. And an element is a unit if it has an inverse. And we usually write the inverse element X is a to the power 1 minus 1. This means the multiplicative inverse of A. And we now come to another important definition. A field this deserves to be highlighted. A field is a commutative ring in which every element A in R different from 0 has an inverse. Now, you know lots of examples of fields. For example, if we take Q to be the rational numbers, if A is some number R over S not equal to 0, then it has an inverse. A inverse is S over R, because R over S times S over R is 1. So the rational numbers form a field. Z is not a field because, for example, 2 is not 0, but 2 has no inverse. There's no integer you can multiply by 2 to get 1. So the rational numbers form a field, the integers do not. And an extremely important field is that P be a prime number Z mod PZ is a field. The set of congruence classes mod P is a field. We often write this as capital F sub P. This means the field with P elements. Well, we know it's a ring. The congruence classes mod M always are a ring. What we have to show is that it's a field. Every non-zero element has an inverse. So that A plus PZ be in Z mod PZ, and A plus PZ not equal to 0. That means not the congruence class PZ. There exists an integer X such that AX is congruent to 1 mod P. That's our theorem on linear congruences. Because if A is not divisible by P, A and P are relatively prime. So that means if I take the congruence class A plus PZ, and I multiply it by the congruence class X plus PZ, I get the congruence class 1 plus PZ, and 1 plus PZ is always the multiplicative unit in Z mod PZ. So A plus PZ inverse is X plus PZ. So the congruence classes mod P form a field. Let's look at an example. Suppose I take P equal to 5. What are the inverses of all the elements? Well, one plus 5Z times 1 plus 5Z is 1 plus 5Z. So the inverse of 1 plus 5Z is itself. What about 2 plus 5Z? Well, 2 plus 5Z times 3 plus 5Z is 6 plus 5Z, which is 1 plus 5Z. So that means the inverse of 2 plus 5Z is 3 plus 5Z. And by looking at the same equation, the inverse of 3 plus 5Z is 2 plus 5Z. So there are 4 non-zero congruence classes mod 5 with representatives 1, 2, 3, and 4. What about 4 plus 5Z? Well, 4 plus 5Z times itself is 16 plus 5Z, which is 1 plus 5Z. So the inverse of 4 plus 5Z is 4 plus 5Z. Let's do another example. These are fun. Let's take the next prime, which is 7. So 1 plus 7Z times 1 plus 7Z is 1 plus 7Z. So the inverse of 1 plus 7Z is itself. Of course, the identity times the identity is always the identity. So what about 2 plus 7Z? If I multiply it by 4 plus 7Z, I get 8 plus 7Z, which is the same as 1 plus 7Z. So the inverse of 2 is 4, and the inverse of 4 is 2. Let's see, what's the next class that's missing? 3. 3 plus 7Z. What do we multiply that by to get 1 plus 7Z? 3, 6, 9, 12, 15. 15. 3 plus 7Z times 5 plus 7Z is 15 plus 7Z. 15 is congruent to 1 mod 7Z. So the inverse of 3 is 5, and the inverse of 5 is 3. And the last class that we're missing is 6 plus 7Z. If we multiply that by itself, 6 times 6 is 36. 36 is congruent to 1 plus 7Z. So the inverse of 6 plus 7z is equal to 6 plus 7z. Okay. Very nice examples. As an exercise, you might compute the inverses of the non-zero congruence classes for the next two primes, z mod 11z and z mod 13z. Okay. Let me conclude with one very important theorem, which is called the Euler-Fermo theorem. And it says the following: let A be an integer relatively prime to M, then A to the power phi of M is congruent to 1 mod M. Phi of M is the Euler phi function. And a corollary of this is in the special case when the modulus is a prime number. If P doesn't divide M, if A and P are relatively prime, then A to the power P minus 1 is congruent to 1 mod P. And so for all A to the P is always congruent to A mod P. So this is a very beautiful, very famous theorem in algebra. So how does the proof go? Well, suppose that we take a reduced system of residues mod P. A reduced system of residues consists of one integer from every congruence class relatively prime to P. The number of congruence classes relatively prime to M is phi of M. So suppose R1, R2, up to R sub phi of M be a reduced system of residues modulo M. So this means that Ri and M are relatively prime for I going from 1 up to phi of M. And if I are different from J, then Ri is not congruent to Rj mod M. So we need to use the following little result I'll call a lemma. If A is relatively prime to M and B is relatively prime to M, then AB is relatively prime to M. This is Euler's lemma. We proved this already. Sorry, not Euler. This is Euclid's lemma. So let A be relatively prime to M, then ARI is relatively prime to M for all I. And if ARI is congruent to ARJ mod M, then M divides ARI minus ARJ, which is A times RI minus RJ. But the fact that A and M are relatively prime implies then M divides, oops, should have moved this up. So let me just repeat this. Suppose A is relatively prime to M, then by Euclid's lemma, A times Ri is relatively prime to M for all I. Suppose that ARI is congruent to ARJ mod M for some I and J. This means that M divides ARI minus ARJ. Factor out the A, it divides this. But if M divides a product and it's relatively prime to one factor, it divides the other factor. So M divides Ri minus Rj, which means Ri is congruent to Rj mod M, which implies that I is equal to J. So what this shows is the following. If R1 up to R sub phi of M is a reduced system of residues modulo M, and if A and M are relatively prime, then AR1, AR2 to AR sub phi of M is also a reduced system of residues modulo M. So you can look at this like this. Imagine you have R1, R2, R3, up to R sub phi of M. So these are integers, all relatively prime to M, and no two of them are relatively prime to each other. And then we have the integers AR1, AR2, AR3, up to AR sub phi of M. And these integers are also another reduced system of residues mod M. So if you take any congruence class relatively prime to M, it has a representative in this row and also in this row. So let's say maybe this and this correspond to are elements of the same congruence class. And in fact, we can pair these off. So every integer here is congruent to an integer here, and this is a one-to-one correspondence. So if you look at this modulo M, the product of all these numbers, AR1, AR2, AR3, up to AR sub phi of M, is congruent to R1, R2, R3, up to R sub phi of M, mod M. And these are just integers. I can factor out the A's. I have A phi of M times A phi of, to the power phi of M, R1, R2, R3, up to R sub phi of M, congruent to R1, R2, R3, R sub phi of M, mod M. And this integer, we can cancel them. So therefore, A to the phi of M congruent to 1 mod M. That's the proof of the Euler-Fermo theorem. And if M equals P, a prime number, then phi of P is p minus 1. If we take the integers 0, 1, 2 up to p minus 1, this is a complete set of residues mod p. This is the only one not relatively prime to p. We have p minus 1 numbers left. So this means that a to the p minus 1 is congruent to 1 mod p if a and p are relatively prime. Okay. So we actually did quite a bit in this lecture. There is a lot to learn, but it's all important. It's all fundamental, and takes a little bit of work to figure it all out, to understand it. So we need to spend some time. That's it.